All right, welcome to the third videos where we're going to look at some actual computations of the inverse Laplace transform of expressions that looks like this. Okay, so based on the comments that I make on the second videos, I think you should be able to understand what is happening here, right? So first thing is that we need to split this apart and we need to check the degree. Degree 1, degree 3, so this is good. The numerator has smaller degree than the denominator, so which means that we can just simply take a look at this and put it here, take a look at this and put it here, right? We don't really care about this one, okay? We only care about the first time when we check their degree. So the degree 1, right, is here, degree 1 polynomial, multiply everything out. This is degree 3 polynomial. After that, I don't care about what this thing is, okay? It have no bearing on what is going to happen next. What is important is this expression here, s plus 2, so you write here, and then s squared plus 4, which you know from the previous video cannot be further factor, and then you have to write here. And then you do this, right? Degree 1 polynomial, 1 degree less than it, just a number. Degree 2 polynomial, I need 1 degree less than it, so it's going to be bs plus c. So the entire splitting, okay, has to be like that. That's what partial fraction, the method of partial fractions tells you. Okay, all right. So now our jobs is to find a, b, and c, and the things that we do is we come back to this equation, multiply this entire expression here and here. So basic cross multiplications, and then through cancellations, you will get here. Okay. And you just need to do whatever you need to do to find out all those coefficients. So one way is to regroup everything, right? Let's collect all the terms that has s squared in it. Collect that's s squared, right? If you multiply, collect all the terms that has just s in it, which means that there's nothing here because there's no s in it. Here we have this thing, right? That's 2bs. Right here we have cs, so that's why we have that. So you basically collect the terms. You can either do it this way or you can just simply multiply everything out and then just regroup, okay? However you do it, you should get an expression that looks like this. And then now you do the comparing coefficients methods, right? So this has to be true for all the s, and this thing only happens if the coefficient matches, right? So this one here better matches with 1. This one here better matches with 0. So is this, because what we are going to say is that this one here should match with something that is like this, right? Because it's supposed to be just s, right? So if you compare their coefficients, this one has to be 0, this one has to be 0, this one has to be 1. So some simple algebra, just solve these 3 equations. 3 equations, 3 unknowns. You know from high school this is solvable. And the answer you get is 1 over 4, negative 1 over 4, 1 over 4, and 1 over 2. So you put them back into here, right? You come and update this. This is negative 1 over 4 now. B is 1 over 4, right? C is 1 over 2. And then you can write them like this. Okay, so now it backs to the situations where we look at that we were looking at on Thursday, right? So we can take out the negative 104 because inverse Laplace transform is linear. Same as this, the number can be taken out. Same as this, the number can be taken out, right? And then we have to do the inverse. So this part is straightforward. This part is from the table. We know is this immediately. This part is also directly from the table. We know that the Laplace transform of cosine kt is s over s squared plus k squared, right? So reading it backward, we know that this has to be this. This thing here, we need to do something, right? So this part right here is not direct. So let's take a look at this particular part very quickly. So let's say you're taking the 1 over 2 out, right? So only this part. Okay, so this part. So you're taking 1 over 2 out. So the inverse of 1, okay, s squared plus 2 squared. So what we know is the Laplace transform of sine kt has to be k and then s squared plus k squared. So our k is obviously 2. So I need to put a 2 here. Okay, but I changed the equation already because previous is 1. So I better do this, right? And this 1 over 2 can be taken out again. So now you get 1 over 2 times 1 over 2, which is why we have something like that. And then this part give you this. This part give you this. Okay? Obviously, if you don't follow this, the best way to do it is not to trust what I'm saying. Just start from here. You know the techniques already, all right? And then do the computation yourself and see whether you can find the A, B, and C. If this is something you're comfortable with, the only thing that you are not comfortable is how to do the inverse. Well, you will start from here, right? And then try to see whether you can get the answers that you're supposed to get, which is right here. All right, so this is a little bit more complicated than the simple stuff that you saw earlier, right? So let's take a look at this thing again. That's another example. Okay, so this example here, we are looking at how to inverse transform an expression that looks like this. So let's take a look. First thing you do is you look at the degree. Okay, that will tell you whether the following step is legit or not. Okay, all right, so let's do that. Degree 2 polynomial on the top. If you multiply all this thing out, it's a degree 3 polynomial, right? Because you have s cubed if you multiply all this thing out. So when it's like that, you know you can split them. In Calc 2, you'll see an example where the top has higher power, you can split them. You have to do long division first. This thing doesn't happen in 252, but I just wanted to tell you so that you won't make the mistake like, oh, it always is splittable in this fashion. It's not necessary, okay? All right, so here, let me back to this. Degree 2 on the top, degree 3 on the bottom. We know we can split it. And this thing here, again, whole nose bearing, when we split them, I don't care about this. I just look at this, I put it here. I look at this, I put it here. I look at this, I put it here. So degree 1 on top, constant. Degree 1 on top, 1 degree less than, so constant. Degree 1, then constant. So multiply everything across, all right? And then solve for A, B, and C. Solve for A, B, and C. So this one, you don't have to do a lot of manipulations. Take all this thing out because inverse is linear, so you can split them like that. Inverse one term at a time. Take the number out. This thing here, you don't have to make any changes. That's that. Directly read from the table. You know this is this. You don't have to do much changing, and then this is done. Okay, so that's that example. So now you have 2 examples, and I think we are good to look at what happens to the Laplace transform of derivative. Okay, so let's do some signposting here. This is something that we kind of need to do, especially with the videos and everything. So let's do some quick signposting. Okay, here. So we done this. Okay, so we have, well, come on. Okay, so we have done this. Okay, we know how to do the inverse. All right, these are the basic inverse, but obviously these are the basic inverse. But obviously things can get out of control. It can be more complicated. We know how to use partial fraction to break them into pieces so that we can apply all this formula. You saw multiple examples already. And now we need to complete this entire program, okay? So we need to complete this entire program, which is, again, back to here. We need to complete this entire program. We know how to do the forward Laplace transform, okay? We know how to do that already. We know how to do the algebra, okay? Partial fraction, we know how to do it. We know how to inverse transform, okay? So we are basically, we have done equipping ourselves on all the basic tools that we need to solve differential equations. The only things that we don't have is that if you look at the tables that we got, okay, there's no derivative, okay? These are just function of t. when we solve differential equations, we will have, say, derivative like that, right? So let's say, for example, e3ty equals to sine t, something like that, let's say. Okay, so differential equation has derivative. That's the reason why they call differential equation. So we know how to transform function in t, all right? But we need to know how to transform a function of derivative before we can complete the program, right? Laplace transform methods. So we need to introduce you to the concept of the Laplace transform of derivative. And in the next video, you can see, once we know that, we can finish all this thing in one example. Okay, so we'll be able to do differential equations, transform everything, including the derivative, partial fractions, transform it back. Okay, so that will be on the next video. I'll see you there.